Hello. So today we will continue with talking about crystals. Okay. So we will learn more how to describe the crystals and what are specific crystal types that we are interested in this course. Okay. So in the previous lecture, we introduced some useful definitions from what is a crystal, what is a lattice, what are primitive lattice vectors, what's a unit cell, primitive unit cell, non-conventional unit cell. We also introduced a Wagner site cell. And finally, we introduced the basis. And we concluded by saying that if I know the lattice and the basis, then I know everything about my crystal structure. Now we can move on to what we are finally building up to, which is 3D lattices. Okay, so there are 14 different 3D lattices. Okay, there are 14 different 3D lattices. These are triclinic, monoclinic, orthorhombic, tetragonal, rhombohedral, cubic, hexagonal. Okay, and cubic, for example, there are 3 types. Tetragonal, there are 2 types. Orthorhombic, there are 4 types. Okay. Now, if we look, for example, let me just teach you how do we name these? How do we define each one of these? So here, every lattice, it has sides. Okay. And there are angles. Okay. So the sides, we call them axes, and there are angles. If all the sides are different, that is, the length of this side is different than the length of this side, different than the length of this side, and all the angles, alpha, beta, and gamma, are different, then we say this is a triclinic lattice. Okay? A monoclinic is a variant of a triclinic, where still all the sides are different in size, okay? But 2 of the angles equal to 90. So 2 of the axes are perpendicular to each other, but 1 axis is not. So that's a monoclinic. There is a simple monoclinic where this is how we describe it. And there is a base-centered monoclinic where, in addition to the monoclinic, we add 2 more lattice points, 1 at each of the 2 bases. Okay. Let's look at an orthorhombic. We will not look at all of them. Okay, let me just now talk about, for example, the orthorhombic. So in the orthorhombic, I see here I have A different than B different than C, which means that we have the sides of the lattice are different. Okay, so A different than B different than the height C, but all the axes are perpendicular. Okay, all the axes are perpendicular. A base-centered is a variant of our orthorhombic. The only difference is that we add 2 more lattice points at the bases. A body-centered, sorry, is another variant where we add another lattice point in the center of the lattice. Okay, and the face-centered is another variant of the orthorhombic where I put a point on the center of each of the sides. Okay, so now you learn how we define any of these. So let's look, for example, at a tetragonal. What is happening at tetragonal lattice? I have 2 sides here are equal. So 2 sides are equal, but 1 side is not equal to these 2 sides. So I have 2 sides equal and 1 side different. And all the angles, all the axes, they are all perpendicular to each other. So all the angles are equal to 90. Okay. And the last one, which is also very important for us, is the cubic case, where we have a simple cubic. We have all the sides equal and all the axes are perpendicular. Okay. And you can look at the other ones and see exactly how do we refer to that. Now, what I want to tell you is that you need to breathe, okay? We will not be learning about all these 3D lattices. We will focus actually only on those where the axes are perpendicular. So we will focus on the cubic, on the tetragonal, and on the orthorhombic. These are the only ones that we will encounter in this course, okay? And mostly on the cubic, actually. Why so? Because in the other cases, when the angles are not 90, it gets very algebraic, it becomes very complicated, and it's almost impossible for us to solve these ones just like this in class, okay? And almost everywhere it's agreed that we stick to 3D lattices with orthogonal axes, okay? We will start with the simplest form of lattices, and these are the cubic. So in the cubic lattices, we have 3 different types, okay? For now, just look at how they look like. We will be talking about each one of them thoroughly throughout this lecture and the coming lecture. There is the simple cubic, where we just look here. This is how a unit cell look like. So there are 4 lattice points at each, 1 lattice point at each edge of the cubic lattice. The body center, where I also have 1 lattice point at each edge of the cube unit cell, but there is also 1 atom in the middle. And the FCC variant is where I also have these 4 corners occupied by 4 atoms, but each side has an additional atom in the middle, or an additional lattice point in the middle. Okay, let's start with the simple cubic. So a simple cubic has other names. We call it primitive cubic or cubic P. Okay, so you need to know these names. If we say primitive cubic or cubic P, then we mean simple cubic. It looks like this. This is how the lattice look like. And if we look at the unit cell, it simply looks like this. So it's a cube. Okay, how many lattice points are there here? How many lattice points are there here? There is 1 lattice point. Okay, there is 1 lattice point. So if I have a unit cell with 1 lattice point, implies it is a primitive unit cell. And it's 1/8 times all of the 8 corners. Okay, so here there is 1/8 of a lattice point. Here there is 1/8 of a lattice point, 1/8, 1/8, 1/8, 1/8, 1/8, and 1/8. If I add them up, it gives me 1 lattice point. Okay, we can write down the lattice points in a more proper way. That is, if I want to reach any point in the lattice, so we refer to this as R, remember, this is equal UVW times the lattice edge line A times the lattice edge line A, where UV and W are integers. Now we were told that we should be able to write lattice points as integer sums of PLV. Remember this? We should be able to write A1, A2, and A3 as integer sums of the primitive lattice vectors. So we can choose A1 to be A1, 0, 0, A2 to be vector A2 to be A0, 1, 0, and vector A3 to be A0, 0, 1. Okay, these are, remember, these are primitive lattice vectors. Fine. So this is how we describe any point in the lattice. Now I'm gonna introduce a new definition. It's very useful for us to know, and that's the coordination number. The coordination number, Z, it's the number of nearest neighbors of any atom on the lattice. Okay, so if I look at any atom on the lattice, let's take this point over here. Let's draw a sphere on top of it just to see it clearly. Okay, how many nearest neighbors does this point have? It has 1, 2, 3, 4, right? 5, and 6. These are the nearest neighbors. Notice this one is not a nearest neighbor. It is not a nearest neighbor. This is A, this is A, if I calculate this distance over here, it is higher than A. Okay, actually, if I take this triangle, it is right triangle. So the the hypotenuse square is equal to A square plus A square. So it is 2A square. So this side over here is A square root of 2. So it is higher than A. Okay, so this is not a nearest neighbor. So the nearest neighbor in a cubic lattice, Z is equal to 6. Okay, now this is how it looks like. This is how it looks like if we put atoms on the position of each lattice point. Okay, it will look like a cube, obviously. Now, although it's a very simple lattice to describe, it's actually extremely unusual in nature. Of all the materials, of all the atoms in the periodic table, only one element, which is polonium, takes a simple cubic arrangement. Okay, so this is the only atom, polonium, that takes a simple cubic lattice arrangement. Before I move forward, I will just mention it briefly that polonium was discovered by Marie Curie, and she named it polonium after her homeland, Poland. Okay. Now, why it is extremely unusual to have this stacking or to have this arrangement? The reason why this is so unusual, I want you to imagine stacking spheres, like stacking tennis balls, for example, in a box. Okay, so bring tennis balls and try to stack them in a box in this arrangement. Okay, it's almost impossible for the balls to stay in such position. They really want to fill this hole in the middle. There is lots of extra space, and some of these balls will just fall into the hole. Okay, so it's almost impossible to stack atoms in a cubic arrangement, and that is why it's very rare to find any element with this arrangement. It's only polonium. Another way to think of it is there is a bonding force that wants to get these atoms fairly close to each other. Okay, so these atoms are attracting each other. There is a force attracting these atoms to each other. Okay, and they want like to leave this space in the middle unfilled. There is something attracting these balls to each other, and it is almost impossible to leave this space over here unfilled. So this is why simple cubic lattice is very, very unusual among pure elements. Now, there are some variants on simple cubic lattice that we need to know. We have the tetragonal lattice. Which means axes are perpendicular and two edges are equal. So if we compare a simple cubic lattice unit cell where we have 3 edges are equal and all axes are perpendicular, in the case of the tetragonal unit cell, we have 2 sides are equal, one side is not equal to them. So I have here A, but this is C, different than A, but all the axes are perpendicular. Okay, so this is a lattice where all axes are perpendicular. And remember, I told you in this lecture, in this course, we will only focus on lattices where axes are perpendicular. And the other variant is the orthorhombic lattice, where all axes are perpendicular, but no edges are equal. So we start with simple cubic, all edges are equal. Tetragonal unit cell, 2 edges are equal, 1 edge is different. And finally, the orthorhombic, the 3 are not equal, but still all axes are perpendicular. Now, although simple cubic is extremely rare in nature, there are things that are based on simple cubic that are quite common. So we need to know about the simple cubic lattice. The first structure we will be discussing is what is called the cesium chloride structure. Okay, why is it called cesium chloride structure? It's a very important structure, and it is named this way because the material cesium chloride takes that structure. Okay, so any structure that looks like a cesium chloride structure, we say it has a cesium chloride structure. Now, this is how a unit cell for a cesium chloride, this is how the unit cell for cesium chloride look like. What do we have? We have a simple cubic lattice. We have a simple cubic lattice. Look, we have a simple cubic lattice, but with a basis. And what is the basis? We have cesium in the corners and the chloride at half. That is in the middle of each cube. Okay, so the cesium chloride structure is a simple cubic lattice, okay, with a basis that has cesium at the edges and the chloride, the red thing over here, in the middle. So it is at half. Okay, if we want to calculate the coordination number of any point in this cesium chloride structure, how much is it? For example, if we look at chloride in the middle, what is its coordination number? That is, what is the number of nearest neighbors? It is 1, 2, 3, 4, 5, 6, 7, 8. So Z equal to 8, but it is of opposite kind. If this is chloride over here, all these are cesium. So it is of the opposite kind. Okay. You might think of it that way, as having cesium at the corners of the unit cell and the chloride in the center of the unit cell. But that's kind of arbitrary that we chose it that way. Here is another picture. So let's look here. Let's assume that the whites are chlorides and the greens are cesium. And now let's look at this unit cell. So this unit cell is similar to the previous one. We have chloride, we have cesiums, the white ones at the corners of the unit cell, and I have chloride in the middle of the unit cell, the green one. But I can look at another unit cell over here, okay, where I can see that I have cesium, the green ones, at the corners and the chloride at the center. Okay, so here I have two depictions of the cesium chloride lattice structure. Okay, and we can view them as two interlocking simple cubics. What we have is two interlocking simple cubic lattices. One of them is made up of cesium, one of them is made up of chlorine. Okay, this cesium chloride structure is a quite common structure in nature, and this is why we study it. Now, over here, you can see, for example, this is another way to see it. The blue ones are cesium, for example, and the brown ones are chlorides. So you can see, if you only look at the green ones, you see that I have a simple cubic structure made up of these cesium atoms. And if I look at the brown ones, I find another simple cubic structure made up of chlorine atoms. Okay, so I have two interlocking simple cubics. This structure is quite common in nature, and we can find beryllium copper, aluminum nickel, all these structures, cesium chloride, all these have exactly the same structure. So we say that beryllium copper has cesium chloride structure. Okay. Now we can do something else. We can look at pure cesium. So again, let's look at cesium chloride. We agreed that cesium chloride is a simple cubic with a basis where I have cesium or chloride at the edges, and chlorine, cesium chloride, and chloride or cesium in the middle. Okay. Now, what if I look at pure cesium? Can I say that cesium by itself, it is simply cubic with bases where I have cesium at the corners of the unit cells and cesium at half, half, half? In other words, what we are gonna do is take the same cesium chloride structure, get rid of the chlorine atom in the middle or the cesium in the middle, whatever we call this one, and put instead of it, so get rid of this chlorine in the middle, cesium chloride, so get rid of this chloride atom in the middle and replace it by cesium, okay? This by itself, if I look at it, is another very important type of lattice that we will be studying. It's known as the body-centered cubic lattice, or what we refer to as cubic eye. Okay, so this is how it looks like. The unit cell looks like this. I have cesium at the edges, at all the edges of the unit cell, and I have another at all the edges of the lattice, and I also have another cesium atom in the middle. Okay, how many lattice points are in this unit cell? So I have one here, right? And then I have 1/8, 1/8, 1/8, 1/8, 1/8, 1/8, 1/8, 1/8. So that's 8 times 1/8 plus 1. So I have 2 atoms in this unit cell. So it is not primitive, it is conventional unit cell. Okay, so it's a unit cell of a body-centered cubic lattice. We refer to it by BCC, and we note it by cubic I. So simple cubic is cubic P. BCC is cubic I. Okay, all the environments, I'm claiming here that all the environments of all of the points is exactly the same. And this is why we said it's a lattice by itself. Okay. What we see here is another convenient way to describe these 3-dimensional structures, okay? We call it a plan view. We call it a plan view. How do we draw the plan view? A plan view is simply, we bring this structure and we look from the top. So we look from the top, from here, okay? If we look from the top, what do we see? We see these 4 corners, right? Underneath them is another 4 corners, but they don't appear because they are just underneath them. So we don't see these ones here. We only see these ones over here. And we see this point exactly in the middle. Okay, we see this point exactly in the middle. So a plan view is looking from the top, and we indicate the heights of all the things that we see. So this point is at what height? This point is at height A/2. So we refer to it as A/2. Okay. Now, these points are at what heights? They are at heights A. These points are at what height? They are at height 0. So the one I label is at height A/2, and the ones I did not label, they are at heights 0 and A. Okay, so in the case of BCC, or body-centered cubic lattice, we will see 4 things in the corners and 1 thing in the center, and then we label the height. So we will see, again, we will see the 4 corners and 1 thing in the center, and the central point is at height A/2, and the corners, they are at height A, and at height 0, and they are unlabeled. Now, if we put the atoms together in this body-centered cubic structure, it will look more like this. Okay, so if we put atoms in the positions of the lattice points, then we will get a structure that look something like this. And we can see directly that this is a more efficient sphere packing, right? So it's clear that it's filling up the holes, okay? The holes are filled, which implies we have much more efficient sphere packing, and there are quite a few materials that take this BCC form: sodium, lithium, iron, potassium, and many, many more. Again, what is the coordination number in case of a BCC? Do you remember what is the coordination number in case of a simple cubic? We agreed it is 6, right? Now, how much is it in the case of a BCC? It's very easy to see it if we take this point over here. So if we take this point over here, where are the nearest neighbors? I have this one, this one, this one, this one, and then this one, this one, this one, and this one. So if I count them, I have 8 nearest neighbors. Okay. In the upcoming lecture, we will be looking at other important cubic structures, namely the FCC structure, and we will discuss another very useful structure, which is sodium chloride. Okay, so here we discussed the body-centered cubic structure, we discussed the cesium chloride structure, we discussed the cesium only structure, and the cesium only pure cesium structure, we agreed that it's a body-centered structure. In the next lecture, we will discuss the face-centered structure, and in particular, we will look at the sodium chloride structure. One question I'm leaving for you to think about. I said that this structure by itself, which is a pure base, which is a pure cesium, it's a lattice by itself. Okay. I made the assumption that each point in the lattice has exactly the same environment. And this is one of the 3 definitions we agreed on for a lattice, right? We said that one of the definitions of a lattice is that if I take any point, it will have exactly the same environment like any other point. But here I didn't prove this. So one thing for you to think about, or you can look into Wikipedia or Google or anywhere. So do your research and find why a pure cesium structure is, why a body-centered cubic structure is a lattice by itself. This is the end of today's lecture, and I'll be posting more lectures next week. Bye-bye.